In this next section, we're going to be focusing on performing calculus with parametric curves, which in this case includes finding the slope of a tangent, finding the area bounded by a parametric curve, or finding the arc length of a parametric curve. So all of these things will involve some notion of calculus. Let's start with the first problem, which is finding a tangent slope. So suppose f and g are differentiable functions, and we want to find the tangent line at a point on the parametric curve x equals f of t, y equals g of t, where y is also a differentiable function of x. Well, according to the chain rule, we can write dy over dt as dy over dx times dx over dt. Okay? Because here we're again imagining that y is really a differentiable function of x, so we can find dy dx. And because x is a differentiable function of t, we can multiply by dx over dt. And then we can also here get a formula for dy dx now as dy over dt divided by dx over dt. Or if we're thinking about it, the y was given by g of t, so this is g prime of t. And x was given by f of t, so in the bottom it's f prime of t. Suppose I want to take a second derivative. Well, we have to be a little bit careful here. The second derivative is the derivative with respect to x of the first derivative. Dy over dx, which we found was here again using the same idea as we did before. It's ddt of our first derivative over dx dt. Okay, so notice that what we're putting here for dy dx is really a function of t here. Okay. So there we go. So this is our first derivative that we found, dy over dx, which is going to be in terms of t. So we're taking the derivative of that with respect to t again, and then dividing by dx over dt again. So the derivative of the original x equation. Okay, so let's be careful. It's not just a matter of taking the derivative of dy over dx with respect to t. We have to divide by dx over dt. So let's try an example. Suppose a curve is defined by the parametric equations x equals t squared, y equals y equals t cubed minus 3t. Show that C has two tangents at the point 3, 0, and find their equations. Well, in this case, we're going to want to find dy over dx at the point 3, 0. So remembering this is going to be taking the derivative of the y equation in the top, and then the derivative of the x equation in the bottom. So let's see, the y equation was t cubed minus 3t, so the derivative will be 3t squared minus 3. The derivative of t squared in the bottom would just be 2t. And so then dy over dx evaluated at the point 3, 0. Well, we would now want to think about what would t be at the point 3, 0. So what we should think about is, when is x going to equal to 3? And when is y going to equal to 0? So we see that when t squared equals 3, we get t equals plus or minus the square root of 3. And then we can check here if t equals plus or minus the square root of 3, do we also get 0? And yes, we see that when y is, when t is the positive square root of 3, in fact we do get 0, because here the square root of 3 cubed would be 3 radical 3. Would it be the same if I have negative square root of 3? So let's check. If I have negative square root of 3 here, and then a negative square root of 3 here, then this would be minus here, and it would be plus here, so it would still come out to be 0. Okay, so it looks like here we've got two parameters t that'll give us the point 3, 0. So in order to get the dy dx evaluated at the point 3, 0, we would have to consider two different parameters t. So actually there's going to be two different slopes that we're going to get. So let's consider when t equals positive square root of 3, we get dy over dx would equal to 3 times the square root of 3 squared minus 3 over 2 square root of 3. So that's 3 times 3 is 9, minus 3 is 6 over 2 radical 3, so that's 3 over radical 3. And this, if we rationalize this, it's just radical 3. Now suppose t is the negative square root of 3, we get dy over dx equals 3 times negative square root of 3 squared minus 3 over 2 times negative square root of 3. So again, we'll get 3 times 3 is 9, minus 3 is 6 in the numerator, but here we'll get negative 2 radical 3 in the bottom. So we get negative 3 over radical 3, and rationalizing that we get negative radical 3. So it looks like at the point 3, 0 in the graph, we have two different tangents, one at the parameter positive square root 3 and another at the parameter negative square root of 3. Well, let's figure out what points on the curve will have a vertical and which points on the curve will have a horizontal tangent. So one way we can remember this is that if we have our dy dx equation, we know when this is equal to 0 is when we have a horizontal tangent. So we can take our dy dx that we found in the previous slide, which was 3t squared minus 3 over 2t, and solve when this is equal to 0, which means that the numerator 3t squared minus 3 equals to 0, in which case t squared equals 1, which gives me t equals plus or minus 1. So we have 2 points, t equals 1 and t equals negative 1, that'll give us a horizontal tangent. So let's look at each of them. So when t is 1, we get the point 1, negative 2. And when t is negative 1, we get the point 1, positive 2. So those would be the 2 points in our curve that have a horizontal tangent. So to think about when we have a vertical tangent, that's going to be when dy over dx is undefined. So when we have a vertical tangent is usually when we're going to have 0 in the denominator. So we know that 3t squared minus 3 over 2t will be undefined when 2t is equal to 0. When the denominator here equals to 0, which gives me t equals 0. And that corresponds with the point 0, 0. So we'll have a vertical tangent at the origin. Okay, so far we've collected some information. We have the points now where we have a vertical or horizontal tangent. What if I want to determine where the curve is concave upward or where the curve is concave downward? So we can use the second derivative to figure out where it's concave upward and where it's concave downward. Because when the second derivative is positive, we know it's concave upward, and when the second derivative is negative, we know it's concave downward. So let's practice taking the second derivative now. So we know the second derivative is going to be the derivative with respect to t of our first derivative divided by dx over dt. So we're going to take the derivative with respect to t of our first derivative, which was 3t squared minus 3 over 2t. And then we're going to divide that by dx over dt again, which was 2t. One thing I can do actually before I differentiate this is divide each term by 2t, so I don't need to use the quotient rule. So 3t squared divided by 2t will be 3 over 2t. And then here minus 3 over 2 t to the negative 1. Okay, and we see here the derivative will be 3 over 2 minus 3 over 2 times negative t to the negative 1. So I'll write plus 3 over 2 t to the negative 2. And then all of that's divided by 2t. And then let's see, if I divide each term by 2t, I'll have 3 over 4t plus 3 over 4t cubed. And if I combine these two, I would have 3t squared plus 3 over 4t cubed. Now let's figure out when this is positive and when it's negative. So we know that when our second derivative is positive, we're going to be concave up. And so that occurs when 3t squared plus 3 over 4t cubed is positive. And we know that that's going to occur only when t is positive, because notice 3t squared plus 3 is always positive in the numerator. So the denominator will be positive when t is positive. Okay, so we see it'll be concave up when t is positive. When will it be concave down? So we know it'll be concave down when the second derivative is negative. So taking 3t squared plus 3 over 4t cubed, when will that be less than 0? And the same idea here, it's always positive in the numerator, so it'll be negative when t cubed is negative. So when t is negative. So we see it's concave upward when t is greater than 0, concave downward when t is less than 0. So let's finally put all these pieces together to form a sketch of the curve. One thing we discovered was that it had two different points when it's passing through the point 3, 0. That was the first thing we did, was we showed that it passes through the point 3, 0 at t equals negative radical 3, and also at t equals positive radical 3. So it has two different times when it's passing through that point. And we were also given two different slopes that correspond to each of those different times. Another thing we discovered was that it has a vertical tangent at the point 0, 0. So if we imagine a tangent line at 0, 0 will be vertical. We found it had horizontal tangents at the points 1, 2, and 1, negative 2. I'm sorry, 1, 2, and 1, negative 1, 2. 1, 2, and 1, negative 2. Sorry. Okay. So these points here and here were where we know we have the horizontal tangents. And then at these two different times, we have one slope of positive radical 3 and one slope of negative radical 3. So let's imagine now, as it passes through these 4 points, it's going to start here at negative radical 3, where the slope is negative radical 3. It's going to pass through that point where it has a vertical tangent. It's going to curve upward here where it has a vertical tangent. And at 1.12, it's got a horizontal tangent, and then it's going to pass back through here at positive radical 3. So you can see that it passes through these points like so. And we remember that the times when it passes through these different points traces out the curve in this orientation, where it passes through this point here twice, so it creates this loop in the graph.